Okay, so we have another tutorial video for Specialist Maths. We're going to cover some new concepts. In the previous chapters, we went through geometric representation of two-dimensional vectors. So let's find a little space here. Okay, so we were drawing vectors in 2 dimensions, and we're doing operations just based off drawing them out as such. Now we're going to go through and represent vectors in terms of numbers. Now, I've done this in terms of aiding how to draw vectors, and the idea I've spoken already about how you can draw, so for example, vector A from O to A could be drawn as 2 across and 1, 2, 3, 4, 5 up. Okay, that's exactly what we're going to be representing them as when it comes to the new system. So let's draw these freehand. Okay. So here's the topics or the skills that you'll be picking up throughout this. Position translation vectors, unit vectors, I and J, equality of vectors, operations in the form of addition, subtraction, negative vectors and scalar multiplication, magnitude and unit vectors, and vectors between 2 points. So I'm going to start off by just drawing vectors from the origin to A and to B, just like that. Maybe we should employ a ruler like I did. All right, and I'm going to call that vector A and that vector B. All right. So, so if I got these vectors here, the position vector often represents, okay, where's the position of A relative to the origin, where's the position of B relative to the origin, and we're talking about the vector moving from O to A or O to B, respectively. So if I was to work out, for example, OA, the vector, that goes from O to A, well, that will be the coordinates of A, which would be A1, oopsies, A2. Okay, that's the position vector, or the translation vector if you prefer. And likewise, OB is B1, B2, as such. So that's how we represent the path that we take to go from the origin to A and to B. Okay, and those are the coordinates, and that's why. All right, so this is the common format we're going to be using for vector notation is, there's X and Y. So translating by this magnitude in the X direction, and if it's positive to the right, and this in the Y, so if they're both are positive, A1 to the right, A2 up, B1 to the right, B2 up, but there are some vectors going down, as we can see, so B2 would actually be a negative value. All right, now when we're talking about this in terms of component form, we're going to introduce a couple of vectors, the unit vectors. I moves you 1 unit in the X direction, is represented as such. J moves you 1 unit in the Y direction, is represented like this. Okay, so you can write other vectors in terms of I's and J's, and we're going to have a bit of practice of that later on. So we're going to go through, we'll do some of the example questions as we go through this stuff, but I thought I'd introduce these concepts. So equality. Okay. If we say, for example, that OA is going to be equal to BC, that means that BC must equal the components. So then BC must equal A1, A2, and then hence, I'm going to say hence, find coordinates of C. So I'm actually setting up this to be a parallelogram, and I'll show you. That's some in the future lesson parallelograms are kind of nifty because you can see some particular features in the rhombus. There's even more features that are special when it comes to vectors. Okay, so let's see if we can find the coordinates of C. Well, I can say that if I went to so OC, for example, the vector that will take me from O to C up there, I could travel from O to B, which I know in terms of B, and then B to C. Okay, so O to C could be expressed as O to B plus B to C. But that can be written, as O to B plus okay, plus B to C, which is also OA because it's equal. Now, we're going to learn another skill here. We're going to learn vector addition while we're doing this. All right, vector addition, thereby, will give us this. OB is B1, B2, plus, okay, now we're going to add OA, which is A1, A2. So we've got the X component at the top and the Y component at the bottom. You just add these. That's all you have to do. Vector addition, B1 plus A1, B2 plus A2. And that's it. So that is actually the coordinates of C. So I actually could write that out here. Go back to over here. Probably don't have enough space to really fit that in, but I'll give it a try. B1 plus A1, comma, B2 plus A2. So now I've got the coordinates of the other part of the parallelogram. All right. So you could also prove that if that was the case, you could also go back and prove that A to C is equal to O to B. And maybe we'll do that later on. So that's how you do vector addition. And maybe we should prove that for vector subtraction. The way we could do that, I think we can. Okay. Okay. Well, we're going to jump to, if we're going to do that, the vectors between 2 points. Okay, let's what is AC? So let's figure that out. Well, using the diagram, I could go from A to C. I could go from I could go around that way. Or, so if I went, I have to go minus A and then OB, OC. So let's figure that out. Okay, so I have to travel from A to O plus O to B plus B to C. Actually, no, I don't need to do that anymore because I've already my eraser through. Okay, I've actually already worked out O to C. Okay, so basically that is, now if I actually do that, OC, I already know what that is. So I'm just write this OC. I'm just going to swap the addition plus AO. Now, but I don't know what I don't have AO in terms of OC. The idea, so now we're going to carry out a subtraction. So I went from A to O, then O to C, which I know. And that will take me basically across from A to C. Sorry, I'm pointing out things I don't know, so I'll repeat myself. A to O, O to C is the same as A to C because it takes you from start to finish. So, okay, then think of this one. Last kind of logical step before we move on. So remember that I'm just going to do the negative of OA, which would be, okay, B1 plus A1, B2 plus A2, plus. Now, if you introduce a negative into here, just times everything inside with a negative value. So A is A1, A2. So minus A1 minus A2. Then just add them as you would usually. So maybe I'll just give myself a bit more space and change the camera direction. There we go. So then just a bit over here. Okay. B1 plus A1 minus A1. B2 plus A2 minus A2. You can see what happens. Well, they're equal to B1. Oh, don't need that extra line. I don't know why I keep doing that. Okay. So yeah, we just demonstrated that and that implies that AC is the same as OB. So I've just shown that the other side is also parallel of that triangle, so that's also parallel. Okay, so it's parallel, 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 parallel. Okay, I'm not going to do anything else with the parallelogram at that point. Scalar multiplication. So if you have the last thing, I think, what are the skills I've got? Let's go back to my list. Okay, so we looked at position, translation, unit vectors, equality, operations, addition, subtraction, negative vectors. Yes, scalar multiplication need to do, magnitude, unit vectors, and I've done that one as well, vectors between 2 points. Basically, if I had, yeah, so if I also did A to B, I do vectors between 2 points. If I did A to B, equals the subtraction of the coordinates, basically. The last coordinate take the first coordinate. So B1 minus A1 and B2 minus A2 in a general sense. You can prove that from the unit vectors, basically. So you've got to start at A, go to O, then O to B. So if you go back to the origin, start at A, go to the origin there, that's basically minus OA plus OB. So that's why it's the final coordinate minus the initial coordinate. And that is because of this. The vector algebra works out that way. Okay, but we'll use some numbers in the future part. Okay, the other things I haven't done, so maybe I'll just do an example, then I'll move on. All right, so if I've got Ka, so I'm going to take a scalar multiplication. That would be K times A1, K times A2. So you just take the amount of X and you times it by K. You take the amount of Y and you times it by K. If it's negative, it also reverse the direction as well. All right, so if you had like 2, it'll double the X distance and it'll double the Y distance as well. All right, now the last one is the length of the vector. Okay, so length, and do I have to cover unit? Yes, I've got to cover unit vectors as well. All right, we'll see examples of all of these, don't worry. I'm just summarizing very quickly how to do everything. All right, so if I took the length of A, well, if I look at it this way, the length of the vector of A is the length of this. So if I thought about it in terms of those unit vectors, so I say I move that many units. Now I've drawn this in a general sense, but if I said it was what was on the grid and every square was 1 unit, then it'd be 2 to the right and 1, 2, 3, 4, 5 up. Okay, so if you got 2 to the right and 5 up, then you've got a right angle triangle here. You can work out the length by using Pythagoras. And that's exactly how it works. So the idea is you take your X component, you square it, just like you would for Pythagoras, and you add it with the Y component and you square it. And then you add them together and you take the square root. So it's just Pythagoras. That's all there is to it. So try that. And the other one, I'll say the unit vector. So unit vector of A. So what if I want to work out that? I want to put a unit vector, so it has a direction of A. With length 1. Okay, and that's scalable because this is why we do it. All right, but I'll explain. How do we do this? Well, if we times take A and we're going to divide by the length. This is going to divide out the length, and you're still moving in the same direction because that's a scalar. It's still moving in a direction, but we're going to shorten it. So in the case, well, it could be shorter than 1 in the beginning, but that would actually lengthen it. 1 over a number smaller than 1 would be larger than 1. But in this case, you would end up with this. Okay, so your x-coordinate would be a1 over the length. And remember the length is this. And a2 over the length. Don't worry, I'm going to go through all examples of all of these briefly. But these are basically how you go about doing all the things that I'm outlining in the sections C, D, let's say again, C, D, E, and F. But we'll go through all these. All right. So let's go through the examples that we see in the book. All right. So you can write any vector in terms of its unit components. So that's just their skill in there. Pointer position vector in here. Okay. So they've got an example here, example 11. Write vectors OA and CB in component form, and hence the unit vector. So assuming that, okay, so C to B, we move 3 to the right, and 1 up. So it's 3 and 1 can be written as 3i plus j. That was CB. Actually, I'm looking at this one. But OA is the same thing. OA, 3 to the right and 1 up. So then these vectors are actually equal because they have the same components. So 3i plus j plus j. Okay, so OA and CB are equal. All right. So, okay, and it's the same basic thing for each of these. For example, you could say E here is -1, 2, 3, 4, 5, 6, and positive 1, 2, 3. So -6, 3. So you'd write that as such. So -6. Let's see my pencil. I'm sure. Maybe I'll move the paper. So then 1e is -6, 3. And that's it. And if you want to write in the unit vector form, then it's -6i plus 3j. All right. Zero in component form. Well, that's kind of simple. 0i plus 0j. It's going nowhere in both components. All right. So magnitude of a vector, let's look at some values for this. Let's go through that one. All right. So if you got like p equals 3 minus 5, 3 and minus 5, then the length of p, take the x component, square that, take the y component, square that. So you got 9 plus 16 square root equals 25 square root equals 5 units. Until it says otherwise, you just express the length in terms of units. It probably being a vector represents something, but without any context, we just call it units. All right, so unit vectors have a length of 1 unit. Now, the traditional unit vectors in one direction, one coordinate direction only, are I, 1 in the x, 0 in the y, and j, 0 in the x, 1 in the y. But there are many, many others. You can have a unit direction in any direction. And so thereby there's actually an infinite set of unit vectors, but they all have 1 unit. So the idea is, okay, if you had something, all right, so if you want to go a unit, if you want to go 1 unit in this, so you have that particular vector, has a length of 1. Well, thereby, the square of minus a third plus the square of k equals 1. You can square both sides, and we also deal with the stuff in the middle. Minus 1/3 times minus 1/3 is a 9th, plus k squared equals 1, because 1 squared is 1. Move that across, k squared equals 1 is 9 ninths minus 1/9 would be 8/9. Okay. Now k, you've actually got two options. You can express, if we take the square root, there's plus or minus 8 or 9. So it could go, there's two directions for that. So if I take the square root, it could be expressed as, you can break up the square root into the numerator and denominator. So the square root of 8 is the square root of 8. And then the square root of 9 is 3. So the k could go up or down, it will still have the same length. So that's the idea that, okay, you go left, 1/3 left, like that. And then you go, or basically, if you simplify that, that's 2 root 2 on 3. Not that that really helps. But it's about, I don't know, square root of 2 is about 1.4, and then double that is 2.8. Divided by 3 is less than 1, but not by much. So you go a little bit, and I've done that. I've done a little bit up, nearly up to 1. And you got another vector, which would be like this. Both of those vectors are legitimate, and they both have a unit of 1. Okay, in total. So this is just an operation of magnitudes. If you happen to have one like this, well, C, 1C, from exercise 3D. Well, and you can just state the length. The length is 2, because it only moves in the 2. Well, what about 1E? 3, not -3, 3. The length is always positive. The other ones, you actually have to carry out Pythagoras. So if it only moves in one direction, that's easy. Okay. So yeah, a lot of them are based on 3 and 4. The sum of the squares of 3 and 4 make the square of 5, and that's why teachers like to use those numbers. But D would actually take some work. So for example, if you do 1D, well, you've got the length of, whatever that happens to be, is the square root of -2 squared plus 2 squared, which is 4 plus 4 is the square root of 8. If you want, that's fine, or the square root of 8 can be simplified into root 4 and 2, and thereby 2 times root 2, if you prefer. And it's called, and don't forget the right units, just out of habit. Okay, which of the following unit vectors? Test them, square both sides, add them up, take the square root, see if they're equal to 1. That one is, you can tell straight away. That one probably is as well, because it looks like if you square both sides, you have a half plus a half, which is equal to 1. Those ones are not. You have 4/9 and 1/9 is 5/9, which will not, on the square root, become 1. And you can try some of the other ones if you wish. Okay, as well. So go ahead and try those. All right, moving on. Okay, so this is where we start to get the business end. So now we're actually able to construct actual vectors. So yeah, as I said, okay, sorry, no, this is actually, we're just doing operations in vectors. So we've done addition, so that, yeah, I already wrote that for A plus B. Yep, you see an example there, x through x in the 1, y in the -3, and then move 4 in the x positive and 7. So add those together, 1 plus 4 is 5, minus 3 plus 7 is 4, and you end up with 5, 4. Okay. Algebraic negative vectors. If you apply a negative, you apply it to both the x and the y as such, and it travels the opposite direction as we went through in the previous lot of work. All right, vector subtraction. Remember, you can work out the subtraction by adding the negative. So thereby, if you use a minus b, then you add negative b. So we've added negative b, a1 plus minus 1, a2 plus minus 2, or just simplified like this. Okay. I'll just do one of those. Okay, so we've got p plus q plus r. Well, we'll have a look at what I've done here. So p minus q minus r. You can see they sort of got 3, take 1, 3 take 1, and minus -2 is plus 2. And same with the y, -2, minus 4, plus 5, and you got the resultant. Okay, algebraic scalar multiplication. If you double a vector, you double both the x and y components. If you triple it, you triple both x and y components. And if you use any fraction, the same thing. So if you take half the length, if you're trying to find a midpoint, you do that a lot. So you take half the length, or you prove that it's half the length. So then you'd have 1/2 of the vector. So then like if I did half of A, it would be 1/2 and 3/2. Okay, so that's the general statement as I went through before. All right. Yeah, if you apply a negative, then it changes the direction, and 0 of a magnitude becomes a 0 vector. That's kind of trivial. All right. Okay, so these operations, you can go through those at your own time. No, I think this is simple enough, so let's move on. You can try these yourself. All right. All right, so maybe I'll pick something like this. All right, so I'm going to contrast question 5. So we're now on, what are we on? Up to part E. We'll go through question 5. All right, so find geometrically. So P plus P plus Q plus Q plus Q. All right, so if you do it geometrically, you just keep drawing them, basically. All right, but and you actually notice that these are all kind of the same thing. Maybe I'll just draw them. I'll see what happens. I might even draw them with pen. Sorry, let's actually show where we're at. So I'll just get that up there. Okay, let's draw some coordinates and let's get this done. All right, so P is 1, 1, Q is 2 minus 1. All right, so if I drew, so number 1, P plus P plus P, so I've gone up to here. The 3 P's, got 1, 1, 1 in the X and Y. No, sorry, only 2 of those. What am I doing? All right, never mind you. All right, so then 2 across, 1 down, so it's P, P, Q, Q, and then 1 more, Q. Okay. So let's try another one. So P plus Q plus P plus Q gets me to the same point. It's not surprising. And then Q plus P plus Q plus P plus Q gets me to the same point. So the idea, basically what we can see from part A, part B is basically the order of addition did not change the result. Because if you notice in all those parts, there's each one there's 2 P's and 3 Q's. All right. So let's have a look at some of the other stuff. All right. Maybe I'll pick something. I'll pick a couple ones out of 7. Let's have a look at 7. All right. So if I find, all right, I've already done lengths. So let's find A is P modulus, which would be 1 squared plus 3 squared equals the square root of 10. Okay, well, what happens if I had B? So B is the modulus of 2P. So what effect does doubling the vector have on the length? Let's have a look. All right, so I have to look at that. So actually, before I took the square root, I should have actually doubled it, but I'll just do this in my head. So we've got 1, 3, which will become 2, 6. 2 squared plus 6 squared. Let's see what happens. 4 plus 36. All right, so square root of 40. All right, interesting, but let's have a look. Can I reduce that? Yes, I can. There's 4 times 10. That can be spread up as different square roots, and thereby is 2 root 10. So doubling that had the effect of doubling the length, which is kind of obvious. But let's have a look at something else. Maybe just pick another one, p in it. All right, if I do, okay. There's no half p. If I do, let's just take e. E minus 3p. Before I actually go and do that, I will actually go and expand that out. So that is going to be the modulus of minus 3. So that'll be minus 3 and minus 9. Okay, and what happens there? Well, square root of minus 3 squared plus minus 9 squared equals 9 plus 81 equals 90, square root of 90, which can be expressed as square root 9 times square root 10 is 3 times the square root. Was that obvious as well? Yeah, the negative didn't have effect on the length, but the 3 did have effect on the length, so 3 lots of root 10. So I think that's pretty straightforward. All right, so let's have a look at the other ones. Vectors between 2 points, so yes, I went through that. The vector from A to B can be expressed in terms of its position vectors. OB minus OA will get you to from A to B, as we can see here. So they've gone through that. So, but just to remember, all right, if you start from A and go to B, then take your B and you minus your A, like that. All right. Yeah, so position vectors, we kind of mentioned those already. Let's move on to something more interesting. All right, I'll take this one for example, question 19. Example 19. Okay, AB is the diameter of the circle with center there, then find the coordinates of A. So A is the other alternate point of the circle. So we've got points for C and B. So we say OC can be expressed as minus 1, 2. And OB is 3, 1. Keep writing that line there. I'm not used to this format. So if we went, if we say, for example, we went from B to C, we write the last point first, and we subtract the other one. So it'd actually be 3 minus 1, 3, or sorry, say 3 minus negative 1 over 2 minus 1 would be, so B to C would be 4. 4, 1. Okay. Now A is not known, and we'll say its coordinates is A on B. As such, I keep writing lines on there like it's a fraction. Get out of that habit. So how can we go there? Well, we can go from A to O to A can be expressed as, okay, find another way to get there. O to B plus B to C plus C to A. Now, but C to A is equal to B to C because they are radii. And they're also going through the center. More to the point, OB plus, it's basically just double. Traveling the full diameter, we just double the traveling from the edge to the radius, and the C is the center. Okay. So OB is 3, 1. I've done it again. Plus 2 BC, 1 gives us, all right, 3 and plus 8 is 11. And then 1 plus 2 times 1 is 3. And that's the coordinate. These are also the coordinates of C. So then, of A. So A is 11, 3. No, it's not. I've done something wrong because I got those different answers from what they've got. That would be because OC. What have I done differently? I've got something backwards. B to C. I wrote those backwards. I wrote this one backwards in particular. So let me swap those two. So it's actually -1 take 3 is -4. That would fix it. Yeah, my boo-boo. I should have actually looked at the example. Okay. So that's fine. Then let's just fix up the rest. All right, so minus. So fix that one up. Okay, so that would be 3 minus 8 is -5. All right, and 1 to 2 is 3. So it's actually -5, 3. That's correct. Okay, I found my mistake. Good. Good to see practice with an example. All right, so let's do the last one, a parallelogram. So that's similar to the one I've been setting up with. All right. So this question form, let's do that together. All right, so question form. Maybe I'll go. There's a blank page I haven't used up yet. Okay, there we go. All right, so we've got parallelogram. So I'm going to do something like this. I'm going to go across like they did. All right, so that goes back 3, like that, and like that. Not quite the same as theirs, but I'll have to do. All right, B, A, B, C, D. All right, so I want to find the corners of D. Okay, so we've got 1, 4, 6, 5, 4 minus 1. Let's give that a go. All right, AB. So if you notice, actually mine is not consistent with the grid because it actually moves in both X and Y. Actually, this one's moving up, but I haven't drawn it moving up. So up to you. Once you kind of get used to this kind of stuff, you don't have to necessarily draw it the way it looks, but sometimes it helps. So if you do it to scale, so if I actually went 1 and then 1 to 6 with 1 up, it would actually look like it's meant to be in the grid. It doesn't matter here though. It does help to get the kind of the correct answers. However, okay. So A, B. All right, so we know that that would be coordinates of B minus coordinates of A. So let's get this right. X, Y minus X, Y equals 5 and 1. Okay, there we go. So we've done that one. Find C to D. C to D equals B to A because it's a parallelogram. The parallelograms, opposite sides are parallel and the same length. So then these two would be equal, and you've got to get the direction correct. So that will be equal to -5, 1, which is -5 minus 1. Oh, I've done it again. What else? Keep doing that out of habit. All right. Hence, find the coordinates of D. Well, if I want to find D, OD, so position vector, so you find the coordinates, equals, we can start from O to A, plus A to B, plus B to C plus C to D. So that will take us from, okay, so that means origin point over there. So we don't have origin as part of this, but yeah, A, B, C, we go across from there to A, B, C, D. Okay. The position of vector of A is 1, 4 plus, okay, we found an AB, which is 5, 1. BC, we haven't done that one so far. It's not too hard. 4 take 6 is -2. Minus 1 take 5 is -6. Okay, plus DC is -1, 5. Okay, well those two will cancel. And then you've got 1 take 2 is -1, and 4 take 6 is -2. All right, so these are the coordinates of OD. So that's a vector of OD, I should say, and the coordinates of D are thereby -1, -2. So put that -1, -2. And we can check that. Okay, if you go from B to C, so you move 5 across, that's 5 across. B to A is 1 down, 1 down. They're both, that's a parallelogram. So that's how you do that one. Okay, so I think that was a list of stuff that I wanted to go through. There's some more examples here. But I think I'll leave parallelism and the other stuff, which is unit vectors. No, I think I said that was on my list as well. Double check. No, I think, what are we at? Did I say F? Yes, let's leave it there. I think that's enough content for this time. We'll save parallelism for next time. So coming up, parallelism, and okay, I think I decided to stop there because it's actually in 2 parts, and this takes a bit of explanation to do. So I think we better save that for next time. All right. But have a try at these ones. So have a try at the questions on 3C, D, E, and F. So you're learning quite a few different skill sets here that eventually you're going to apply to problem solving and vector proofs later on, as you can see as we go through this chapter. All right, so that's going to wrap up my video. So have a go and let me know how you felt.